Okay, so once you have those points in, don't perform a regression just yet. But we're comparing the box width, that's my L1, to the volume of the resulting box. So we're playing around with different widths of boxes, and how's that going to affect the volume of the box? Okay. To wrap your head around this, I want you to consider, draw this out here real quick. Imagine you have a sheet of cardboard, and I'm asking you to make boxes with different widths, right, different sizes, by just using this one sheet of cardboard. How would you do that? Well, imagine some of you are saying, well, I'm gonna cut a square into each corner here, and then if you remove these squares, can you envision you folding up those little creases that result? Like if you fold it here and here and here and here, this is the base of the box, right? And these would be the four sides that make that box. So that's box number one. Let's say someone else has the same sheet of cardboard, but decides to cut up a bigger chunk into each corner. Imagine these are all squares, perfect squares. And all of a sudden, if you now consider the base, it'd be a very narrow base, right? But your walls, the walls of the box would be taller, right? So you got to think about it that way. Okay? So as we do this, like as the box width in this case changes, so does the volume. But did you know that there's the perfect cut you could make to maximize the volume, to get the most possible into that box? And that's where cubic functions come in. Okay? So because we're comparing the width of the box, like actual dimension of the box with the volume, this is a cubic relation. Okay? What type of function do you think best fits the relation between the width and the volume? It is a cubic regression. Okay? Since the width affects the volume, which is cubic. If you think about it, volume is cubic. And you might say, Mr. Dirksen, but you just did a question with gas. Remember the driving and the amount of gas in your fuel tank? That is linear. Like if you drive the same speed the whole time, the amount of fuel that's in your tank is going to drop at the same rate. So we're not talking that scenario. When you're talking either the width, the height, or the length of a box and the volume, that relationship is cubic. Okay, guys? So don't be mistaking, oh, that was volume, that should have been cubic. No, no. Here we're actually talking about one of the dimensions of the box and how is it going to affect the volume. So determine the equation that best fits the volume as a function of width. Okay, we're going to go stat, calculate, cubic regression. Okay, so we're going to come up with our cubic regression. I didn't do the zoom stat, so maybe I should do that. How about we do zoom stat first? There it is. Let's try to come up with the equation now. Stat, calculate, cubic regression, second 1, comma, second 2, comma, alpha, trace, enter, and there it is. Y is equal to negative 0.002 x cubed plus 0.06 x squared. And what about C and D? They are just 0, right? So they're not there, and that's okay. It is okay to not have them there. As long as the x cubed is present, you are fine. Let's graph this. Let's hit graph and see what happens. Okay, question. Could you tell that this isn't a quadratic? Would you be able to tell? Are there some hints that kind of give it away? Doesn't this look like it's slightly going away, like it's not actually following the quadratic? A quadratic should kind of curve, but it shouldn't like veer off like that. It's kind of like asymmetric. So that is a little bit of a hint there if you forget, okay? But let's make sure we change our window so we see more. So window, x-min, I want it to be negative, so -2. Why -2, Mr. Erickson? Why not -3? Okay, fine, -3. Honestly, it's just random. Like I'm not, it will work. Whatever you pick will work. Just make it negative. So y-min and y-min, x-min negative. There we go. Next would be, let's change our x max as well. I'm going to go back to window. X max is going to be 50. Why 50? Just because, okay? And so one thing I want you to remember, if this ever shows up anywhere, the graph for when it comes to volume and any of the dimensions starts at 0, 0, and it will stop right here. As soon as it hits the x-axis, you're done. Even if this had turned back in, like if this turns and comes back into the positives, it stops at the very first x-intercept. That's it, okay? Anything after that is not admissible. It doesn't work anymore. So what's the maximum possible volume of this design? Because we're only considering from here to here, the maximum is going to be found right there at the vertex, so to speak, at the maximum. So let's go find that. Second trace max, left, right, enter, and there it is. Let's write down what it is that we did here. Second trace max, and that is basically 28. Remember, this is the width, and this is the volume. So the max volume is 8 what? What is volume measured in this case? It is measured in liters. It could have been cubic centimeters. So just go off of what they're telling you. So the maximum volume possible, if you get this right, is 8 liters. What width would you need to have to get that volume? A width of 20, and the width is measured in centimeters, so will give the maximum volume. So now you know. You would have to cut out the corners in such a way that the width of that box is 20 centimeters, and now you're good to go. Now you're going to get a box that has the maximum amount of space in it. Okay. What width would yield a volume of 5 liters? Show how you determined your answer. So they're basically saying, what is the width supposed to be if you have 5 liters of volume? That would tell you that y2 is equal to 5. We go second trace intersect. And let's go ahead and do that. y2 is equal to 5, hit graph, and it happens 2 times. Right? It happens here and here. So there's 2 instances where you get a volume of 5. So that's what you would have to do there. Find the intersection. I'll find the first one here. Enter, enter, enter. So that's 11.685 and 26.425. So there's two cases. A width of 11.68 centimeters or 26.42 centimeters will do it, okay? And let's graph this thing. So we compare the width, which is measured in centimeters, and the volume, which is measured in liters. Have we determined the x-intercept already? We haven't done that yet, right? So let's find that on the side here. X-intercept, I don't need you to use keystrokes on this one. Let's just quickly find that. y2 is equal to 0. It equals, we'll find that intersection out there. That's 30, 0, okay? So you found the 30, 0. I'll write down the max here. We already found that as well. That's 28. And the initial is 0, 0. How do I know 0, 0 is part of this? Because D, I don't know if you remember from the equation, D, which is the y-intercept, is 0. So that is definitely a point as well. So in terms of the x, I need to go to 30. So I'm going to go 10, 20, 30, 40. There we go. And here I'm going to go up by 2s. 2, 4, 6, 8. So 28 is the highest point I ever reach. 0, 0 is one point. And 30, 0 is another point. So this is slightly, goes like this. And then goes back down there. This is not quite, I'll try it again. There. And your equation. There you go. Stops at the first x-intercept. Okay, exclamation mark. Make sure you have this little note there. So we don't consider anything past the first x-intercept because then you have a negative volume. You can't have a negative volume, right? So keep that in mind.